Hello everyone, my name is Saurabh Monto and today I will be talking about drying process in pharmaceutical industry. Though this topic comes under the subject pharmaceutical engineering, the content of this topic has been prepared according to the PCI latest syllabus for B.Pharm. The students of diploma or D.Pharm can also follow this content. So without wasting any time, what are the things we will be discussing in this topic? Let's see. On the first segment of this topic, we will be discussing about the objectives of drying, why we usually perform the drying process in pharmaceutical industry. Then we will be talking about the various application of drying process, then mechanism of drying process, then how we can determine the equilibrium moisture content and what is rate of drying. On the second segment of this unit, we will be discussing about the tray dryer and drum dryer, where we will be discussing about the principal construction, working, uses, merits and demerits of each equipment. On the third segment, we will be discussing about the spray dryer and vacuum dryer, where we will be discussing about the same points like principal construction, working, uses, merits and demerits. And then the last segment we will be discussing about the freeze dryer and fluidized break dryer, which is generally used in most of the pharmaceutical industry. Next is an introduction. So drying can be defined as the removal of small amount of water or other liquid from a material by the application of heat. It also includes the removal of volatile liquid or water from another liquid or gas or a suspension. So drying is possible when the environment is unsaturated with water vapor or moisture. So hence humidity is a very important determinant in the drying process. So if there is so much humidity in the environment, then it can affect in the drying process of any material. Next is the objective of drying. So the main or the basic objective of drying process is to remove the relatively small amount of water from solids. Drying process is usually carried out on solid materials like powder, paste, products, etc. If we want to remove the small amount of water from the powder, then we can use drying process rather than evaporation or distillation or any kind of other heat processes. Drying involves the removal of water at temperature below its boiling point, just like the evaporation process. So, in case of the evaporation, the process of evaporation involves the removal of much more quantity of liquid per hour than in drying process. So, when the thermal drying is when we are talking about the thermal drying, right, there is a presence of heat, and when we are talking about the non-thermal drying, non-thermal drying is usually carried out by the freeze drying machine where there will be no presence of heat. So these are the two methods of drying. First method is a thermal drying and non-thermal drying, which we will discuss in the equipments when we are talking about the equipments and various equipments for the drying process. That time we can easily understand these two methods. Again, if you want to read on non-thermal drying, there will be so many things like expression, extraction, adsorption is there, and what are the meaning of those things you can get from the non-thermal drying also. Next is a application of drying. The first application is preparation of or preservation of drug products. So there are so many drug products. If there is a presence of any water molecules in those drug products, then there is a chance of deterioration or there is a chance of degradation. So what we need to do, we need to remove out those products. Like example, in the herbal extract, if there is a presence of any water molecule in the herbal extracts, there is a chance of deterioration in the herbal extract product. So what if there is a small amount of water, then we can go for drying process, and if there is a large amount of water, then we can consider for evaporation. Next is preparation of bulk drugs. Yes, for the bulk drug preparation, drugs in the form of powder, we can use the drying process. Improve handling. If we remove the small amount of water from any kind of material, then the material is free to flow, and we can easily handle those material also. Improve characteristics, yes, definitely. If we remove those water molecules from those material, then definitely the characteristics will be improved. If we'll consider the powder for the tablet preparation, if we'll remove the water molecule from those powders, then automatically the flow rate will be higher, the Hausner ratio will be higher, the compressibility index will be higher, and there will be so many characteristics which will be affected. Reduction in transport costs, yes, absolutely. If there is a presence of any water molecule in any material, and if you want to transport in the sense of packaging and everything, then you need to think about that how you can preserve. But if you will already remove those water molecules from those materials, then definitely you need not to worry about the material deterioration in the presence of oxidation or hydration or this kind of chemical process. Purification of crystalline process products is another application of drying process, and prevention of erosion. Next is a mechanism of drying process. There are various mechanisms of drying process, but these are the 5 basic mechanisms which involve in any kind of drying process. The first one is a liquid diffusion. If the liquid from the wet solid is vaporizes below the boiling point of the liquid, that is called the liquid diffusion, which means that if the liquid from the wet solid, if there is a presence of any solid, and in that particular solid if there is a presence of small amount of liquid, and what we need to do, we need to vaporize those liquid from the solid, and if it will happen below the boiling point of the liquid, then that mechanism or that principle is called as a liquid diffusion. Next is a vapor diffusion. If the liquid vaporizes within the material only, right? Liquid vaporizes within the material only, that is called a vapor diffusion. Next is a condensation diffusion. If the drying takes place at very low temperature and pressure, in case of the freeze drying process, it takes in a very low temperature and pressure, that is called as a condensation diffusion. That mechanism is called as a condensation diffusion. Next is surface diffusion. This is also possible, but not proven till now. Scientists believe that surface diffusion is a one kind of mechanism for drying process, but this thing or this phenomena could not able to, you know, record it theoretically till now. Hydrostatic pressure differences when internal vaporization rates exceed the rate of vapor transport through the solid to the surroundings. So this hydrostatic pressure differences, due to the hydrostatic pressure differences, the drying process can be occurred. So these are the 5 important mechanism of drying process, and for some of the equipment this 5 mechanism is also involved. So if we'll consider about the freeze drying, then condensation diffusion is a one kind of mechanism in the freeze drying, but there are so many equipments like uh, equipments like other dryer, there all this mechanism will be involving mechanism like liquid diffusion, vapor diffusion, condensation diffusion, surface diffusion, hydrostatic pressure differences, etc., etc. Next is a what do you mean by measurement of equilibrium moisture content, or what do you mean by equilibrium moisture content? How we can measure the equilibrium moisture content, and what is the relationship between the equilibrium moisture content with rate of drying? So these are the things we will be discussing in this segment. So first thing is the equilibrium moisture content. It is the amount of water which exerts vapor pressure equal to the vapor pressure of atmosphere, or you can consider as it is the amount of water present in the solid which exerts a vapor pressure equal to the vapor pressure of the atmosphere surrounding it. So based on the condition of temperature, based on the condition of humidity, the solid can absorb the moisture, and solid can lose the moisture. So when the air is continuously passed over the solid containing moisture more than EMC or equilibrium moisture content, then solid will lose the water till the EMC is reached. So this phenomenon is called as a desorption. Means when the air is continuously, suppose there is a presence of one solid, and in that particular solid there is a presence of moisture, and that moisture is more than EMC, equilibrium moisture content, and now air is continuously passing through this solid. Okay, so that solid, what they will do, they will lose water. Why? The concentration of the moisture in that solid is more than EMC, so they will, when the concentration of the moisture in the solid is more than EMC, they definitely lose the water, and when the concentration of the moisture in the solid is less than EMC, then they will absorb some water. They will they will absorb the water, right? And these two phenomena is called as a desorption and sorption. So in this you can see that moisture in solid, if the moisture in the solid is greater than EMC or equilibrium moisture content, then that is called as a desorption. That time the solid material will lose the water. When the moisture in the solid is lesser than the EMC, then that process is called as a sorption, and in that time the solid material will gain some water. For better understanding, you can follow this. When the moisture in the solid is greater than the EMC of the solid, that process is called as a desorption. And when the moisture in the solid is less than EMC of a solid, that process is called as a sorption. At equilibrium stage, the vapor pressure of the weight mass is vapor pressure of atmosphere. So this is a basic thing, and from this part, this desorption and sorption came. These two phenomena came. Next is a free moisture content. Free moisture content are those things, suppose in a material there is a presence of, suppose in a solid material, okay, there is a presence of so many water molecules which are unbound, which don't have, doesn't have any hydrostatic bond with the other molecules. So this kind of water molecules is free to evaporate, free to move, free to do anything. So this kind of water molecule is called as a free moisture content. Now if we want to calculate the free moisture content, then how we can calculate? So free moisture content is equals to total water contained minus equilibrium moisture content. Next is a rate relationship, and from the rate relationship we can understand the what is rate of drying and what is the relationship of rate of drying with the rate relationship. So if we want to understand the rate relationship, then we can mimic a simple model. Okay, so the model is something like that. Suppose if you have a wet slab of solid, and the hot humid air is passing through this wet slab of solid, then the change in the weight is determined by the weighing the slab at different time interval, and following calculations can be made. The following calculations are: first is a loss on drying, which is also called as a percentage on loss on drying. This can be calculated as mass of water in sample divided by total mass of wet sample into 100. Then percentage moisture content, which is also called as percentage MC. This can be calculated as mass of water in sample in kg divided by mass of the dry sample in kg into 100. And from this too we can easily calculate the drying rate. Drying rate is a weight of water in sample in kg divided by time in hour into weight of the dry solid in kg. These are the three very important formula you need to remember, because there are so many questions like MCQ can be asked from this formula only. Okay, so if you know, suppose there is a they are mentioning like total mass of the wet sample is this, so what is percentage on loss drying? Okay, sorry, percentage on loss drying this, then what is the mass of water in sample? So this type of question can be asked in the MCQ in most of the competitive exam as well as semester exam in most of the university. So if you know and if you understand and if you can remember these three equation, then it will be helpful for you. So if we'll consider the moisture content on the x-axis and the drying rate on the y-axis, then we will find this kind of drying rate curve. This curve is called drying rate curve. Here you can see that the moisture content and drying rate, there is a relationship between the moisture content and drying rate, right? So you can see the moisture content in the atmosphere, the decreasing, and the drying rate is also increasing. So this is the moisture content. See, the drying rate is kind of increasing. Now this is a static point, which is also called, this point is called as a critical moisture content. Then the moisture content is increasing, then fast falling rate of drying. This is a fast falling rate of drying, as because the moisture content is increasing in the atmosphere. This is a second falling, and as because the moisture content is increasing. This portion is called as the equilibrium moisture content, which I already discussed in the previous slide, and this is the second critical point. Now next is the equation for drying theory. So in the drying process, both heat transfer and mass transfer takes place. So to understand the drying theory or to conclude the equation for the drying theory, we need to start with the evaporation of any film. Suppose uh, there is a liquid, okay, there is a film of liquid on the surface of any material, and we need to dry those liquids. So there is a film of liquid on the film of liquid, or there is a one single sheet of liquid on the surface of the material, and which we need to dry. Okay, so now the rate of evaporation of this film of liquid, the rate of evaporation of this is related to the heat transfer, and by the following equation, the equation can be concluded as dw by d theta equals to q by lambda, where dw by d theta is a rate of evaporation of water per hour or per minute, whatever the uh, um, unit. Then q is the overall rate of heat transfer, and lambda is a latent heat of vaporization of water. Now with this equation we can conclude it with this second equation. How? Now as we already discussed, right, there is a presence of one material, there is a one film of liquid which is present on the surface of material, and all we need to do, we need to dry the film of liquid from the surface of the material. So we got this dw by d theta is equals to q by lambda, right? Now in the next segment, what we can see that the rate of diffusion of moisture into airstream is expressed by similar to heat transfer via driving forces humidity difference. So if we'll write down in a equation, then it will be like dw by d theta is equals to k dash, where k dash is a coefficient of mass transfer. Okay, so coefficient of mass transfer, though it's a coefficient, but it is not at all constant. Okay, it varies depending upon the velocity of passing airstream, the air which is uh, streaming, the velocity, depending upon the velocity of that air. Next is a is the area of evaporating surface, which is basically we can consider the vessel area of the surface of the vessel from where the evaporation are going on. Then hs is equals to absolute humidity at evaporating surface, and hg is equals to absolute humidity in passing airstream. So this k dash coefficient of mass transfer is not constant, as I told, because it will depending upon the velocity of the airstream, right? And it can also be written as k dash equals to cgn. C is a proportionality constant, G is a rate of flow of air, and N is a fractional exponent. Okay, so after an initial adjustment period, the rate of evaporation and the is equals to the rate of diffusion of water and the rate of heat transfer. So if we will write down this all, then first we had dw by d theta equals to q by lambda. Then we got dw by d theta equals to k dash a hs minus hg. So by if we'll write down, then it can be it they are all proportional to each other. Okay, so they are means here the rate of evaporation, the rate of diffusion of the water and the rate of heat transfer, they are all equals to each other. So if you'll write down in equation, then it will be like dw by d theta equals to q by lambda equals to k dash a hs minus hg. This is the equation number 4. If the overall rate of heat transfer is expressed as a sum of heat transfer by conduction, convection and radiation in equation number 4, then equation number 4 can be expanded like this: dw by d theta equals to qk qc qr, qk qc qr. This is a radiation, convection, conduction, okay, divided by lambda equals to k dash a hs minus hg. Okay, so the rate of drying may be accelerated by increasing any of the individual term in the equation. The rate of drying can be depending upon the rate of evaporation, heat transfer, then velocity of the air. That can be depending upon the so many. And these are the factor like Q, K, Q, C, Q, R, A, H, S, H, G. These are the factors. If we'll change this factor, then automatically the rate of evaporation can also be increased as well as decrease. That will depend. Okay, so this is all about the drying process and drying theory and the way we can calculate this process. Question are generally not asked in the pharma sector, is generally not asked to derive this type of equation, but yes, if there is any kind of short note which can be asked for the exam purposes. So there are two books which I will recommend. The first book is a Pharmaceutical Process Engineering by Anthony J. Hickey and David Ganderson, which is a highly recommended book for any kind of pharmaceutical engineering unit. You can follow the unit number 7 where you will find this drying process. And you can also follow the theory and practice of industrial pharmacy by Lasman Lieberman. And the unit name in that book is drying. You can follow that also. Thank you everyone for listening me. If you have any doubts or question or need any kind of assistance, then you can contact me on this mail ID. Thank you.